everybody. I'm Julia from the Macedon Public Library, and today we have some guests joining us, and our speaker is going to be Brian Koberlein, who is my husband. He's going to be talking about Introduction to Radio Astronomy, and here he is.
This high-tech change on there. Yeah. So it's really going to be kind of flexible. I'll give you a basic
Talk about who you are and what you do.
Background of who I am and what I do. My background is actually in astrophysics, or PhD in physics, but my current job is as a science writer for the National Radio Astronomy Observatory, which is the federal government's radio network, basically, for radio astronomy. And so that's where my background is and how it relates to radio astronomy. Sorry about my hair, it keeps wanting to stick up. I'm getting, I don't know if you've seen the Stephen Colbert home hair, it basically sticks straight up like that. I'm rivaling him now, so that's where it is. So I don't know, as the audience, what you kind of want me to start with. I'm pretty flexible. I could start with a basic overview of what radio astronomy is and how it differs from regular astronomy.
Yes,
okay.
Please.
So, if you know about visible light, it comes in different colors. So you've got, red, orange, yellow, green, blue. And light comes in other colors that we don't see. So ultraviolet, infrared are forms of light. Radio is another form of light. So it is just like any other light. The difference is that the different colors of light are distinguished by what's known as their wavelength. If you think of light as a wave, the closer together the peaks and troughs are, then the shorter the wavelength. And so for visible light is really, really, really tiny. It is on the order of 700 to 400 nanometers. A nanometer is a billionth of a meter. And so visible light is you could say it's on the order of viruses in size, to be somewhat topical. It's microscopic in that sense. So radio, on the other hand, is much, much longer. So radio light that you would detect would be anywhere from the order of about a millimeter or a little bit less than a millimeter, which is the thickness of a dime, up to centimeters and even meters and kilometers if you really want to. So it's a much, in terms of visible light versus radio light wavelengths are huge compared to visible light. So even though they're both light, the wavelengths are dramatically different. And that makes all the difference in the world. So when we look at radio light, we normally don't think of it as light because we think of radio sound, like the sound that you get from a radio station or from your cell phone, which is microwave radio lights. Even television is a radio signal. It's a long wavelength light signal. We don't think of it as light because we can't see it. It doesn't seem to behave like light, but that's what it is. Most of radio experience that we have comes from artificial sources, things that we make in order to use it for radio and television and everything. But in the universe, there are lots of things that create radio light. So the sun, for example, creates radio light as well as visible light. Most of the radio light comes from strong magnetic fields or particles that have collided with gas and dust. Things like that are the types of radio light. So the universe gives off a lot of radio light. Most of it is actually really faint. One of the classic examples you would say is that if you think of your cell phone, your mobile phone doesn't give off a lot of radio signal. It's not particularly powerful, but things in the universe that give off radio light are so faint. If you took a cell phone and put it on Mars, it would be the brightest radio source in the night sky. So radio telescopes have to be really, really sensitive. You have to be able to pick up really faint radio signals. one of the challenges is that in order to capture a faint signal, you need a lot of area. So if you think of an ordinary pair of binoculars or a telescope, when you're looking at visible light, for example, you might know that a small telescope can't capture as sharp of an image as a bigger telescope. So if you've ever done regular astronomy, you know, if you look at, I don't know, say the planet Jupiter or something with a pair of binoculars, you'll see kind of a little disk and you'll see some little lines or something. But if you have, say, a 10-inch diameter telescope, then you can actually see real features. You can see the red spot on Jupiter. You can see the cloud patterns in Jupiter, because the bigger your telescope, the more light it's gathering and the sharper your image. And that has to do with just the relative size. So the reason that works is the size of your telescope relative to the wavelength of light. So if you want to do radio light, since radio light is thousands of times longer in wavelength, if you want the same type of image, you need a telescope that is thousands of sizes bigger. So you have to have these huge telescopes to get really sharp images. And that's hard. So there's two ways that this has been done. The most common way, I'll talk about in a minute, but one way is just to make a bigger dish. And so if you try to make a bigger dish, you get to a point where it's actually just hard to make. So in Green Bank, Virginia, there is basically 100-meter dish, and it's the size of a football field, and it is the largest steerable telescope in the world, and it gets decent images, but that's not a big telescope for radio. And even though it's a football field in size, it's actually limited in how sharp of an image you can get. So how do you build something bigger than 100 meters, 300 feet? Well, one way is to actually build a telescope where the dish is so big you can't steer it. And so Arecibo in Puerto Rico is one of these. If you've seen Contact, the movie Contact, you've seen this big dish that's kind of in a valley. That's Arecibo. If you've seen, there's one James Bond movie that was filmed at Arecibo, where they had the antenna receiver of this kind of mesh dish. I think it's Live and Let Die or something like that. It's not one of the new ones, but in that case, the dish isn't steerable. So you can't look at a whole lot in the sky. You have to let the Earth rotate in order to see more of the sky. In China, they've just built one that's even bigger than Arecibo that is 500 meters across. It's called the FAST telescope. And same type of thing. The dish doesn't move. You can't aim it. And so that is a real challenge for radio astronomy. But in the past, really about 40 years, another way to do it is to, instead of have one big dish, to have a whole bunch of little dishes. So if you've ever seen the Very Large Array in New Mexico, it's been in Contact, the movie, it's been in 2010, it shows up every now and then. It's basically a whole bunch of little antenna dishes, or they're not little, but a whole bunch of antenna dishes that are spread across this plane. And they can spread out to a distance of several kilometers, so they can be adjusted. And those can steer, and they work together so that each of them, when you collect the light, is at the right time so that it acts as kind of an effective dish. It acts like a whole big dish, instead of being a single dish, a whole bunch of little ones. So that would kind of be like if you wanted a big mirror telescope and you had just a couple of mirrors in various places that all work together so that you could create a single source. And that's a process known as interferometry. Basically, you time when every signal goes to each antenna, because as the signal comes in, it hits one antenna before it hits another antenna. And so you have to record the time when the light signal comes to each antenna, and then you have to line them all up. So you have to have a powerful computer to take all of those little data and line them all up. And now that we have a powerful enough computers to do this, this is the main way that radio astronomy is done. They're done with arrays of antennas to create a large area so you can get a really large effective dish, like a virtual dish, by using computing power. So, and that's come on, that's actually made radio astronomy, it kind of revolutionized radio astronomy. Because if you go back and look at early images of radio astronomy, they're really, really fuzzy. You get this kind of blob, and they'll say, well, that's the planet Jupiter. And you get, here's this blob, and it's like, well, I guess it's kind of roundish. Okay. You know, if you go back 30 years, the images of radio astronomy just aren't that interesting. Because most of it was just using the information. They weren't creating images because radio telescopes weren't powerful enough to really make images. Now we've got arrays of telescopes that are so powerful, we can create radio images that are as sharp as the Hubble telescope. So all of those great Hubble telescope pictures of galaxies and nebula and all of that, you can now make radio images that are that sharp, because we now have arrays of radio dishes to create these virtual things. And in fact, one of the latest things we've done is connect a whole bunch of different observatories, radio observatories all over the world. And we were able to create an image that was so sharp, we could see the light scattered around a black hole. That's kind of like the biggest discovery that radio astronomy has done. And in order to see that, in order to see this little tiny black hole a million light years away, you had to create a virtual radio antenna the size of the Earth. So you connected all these radio observatories through interferometry to create this virtual radio dish that's the size of the Earth.
Cool. Oh, yeah.
So that's kind of the background of radio astronomy. I could go into, I guess, why do radio astronomy when we have visible astronomy? Why even bother with this if it's so hard to do? And there's a couple of things that make radio astronomy very powerful. One of them is that with visible light, you're seeing either what is emitted by hot objects or reflected off of objects. So visible light, you can see things like stars that give off their own light, like the sun. Or you see light reflected off of a planet or off of a gas cloud. And so while you can see a lot of detail, you only get those light sources. If something doesn't create visible light, you can't see it. So you don't know necessarily what it's about. So as an example, if you look at clouds in the sky, all you can see is the light reflected off of those clouds, invisible light. So all you're seeing is the surface of the cloud. You can see the shadows of sunlight over the cloud. You can see where the sunlight is reflecting, but you don't know how deep the cloud is. You don't know what the cloud is made of, other than the fact that we know that it's made of water. But by just looking at it, you can't tell what it is because you're limited in what's being there. Radio light, because it's so much of a longer wavelength, it actually goes through most of things like clouds. And so things that we couldn't see with visible light, we can see with radio. So one big example would be if you look towards the center of the Milky Way, what you see is a huge dark gas cloud. In visible light, you just get a dark patch. In fact, there's so much gas and dust there that in the southern hemisphere, they have constellations that are dark clouds in the Milky Way. When you look at the Milky Way, you see dark regions. And they'll say, well, this dark shape in South America, for example, this particular dark shape is the llama. And this is the loon, or whatever, depending on which culture you're talking about. But because there's so much gas and dust, you don't see the center of the Milky Way. You just see gas and dust. You see a dark region. So if you want to know what's in the middle of the Milky Way, visible light doesn't tell you. You just don't know, because all you see is a cloud. But with radio light goes through the cloud because it has a longer wavelength, so it doesn't scatter, it's not absorbed. And so anything that's creating radio light in the center of the Milky Way emits this radio light, and it goes through these gas clouds, and we can detect them with a radio telescope. So one of the things we can do is that stars create radio light. And so we can look at the center of the Milky Way with a radio telescope, and we can see stars that are hidden in the clouds that are giving off radio light that we can see. And we can actually see these stars orbiting this very large mass in the center of the Milky Way. So that's one of the ways that we know that there is a large black hole in the middle of our galaxy, because we can see these stars orbiting year after year, this really massive black hole. And we wouldn't be able to see that without radio light. So that's one of the things. Another thing is that there are many things that don't give off visible light but do give off radio light. So as an example, cold gas and dust, cold dust, for example, emits a glow of light in the same way that if you heat something up, it starts getting an orange glow. Well, this gas and dust is so cold, it does glow, but it doesn't glow in visible light, it glows in radio light. And so with a radio telescope, you can look at a region of gas and dust and you can see how big are the dust grains and how are they moving. So one of the big things with radio astronomy now has been looking at how planets form around other stars. So you can look at, say, a star that's surrounded by this gas and dust. And normally you wouldn't really see much, but with radio astronomy, you can actually go and see the patterns in the dust. And in fact, because we can get high resolution images now, you can actually see gaps in this disk of dust around a young star where planets are forming. And what the planets are doing is they're sweeping up this gas and dust. And you can see, oh, see, there's 5 gaps. So there's 5 planets forming in this young star system. And we have hundreds of images of these young star systems now. So that's kind of the big thing about radio astronomy is the ability to capture high resolution images now and to process them means that we can do things we couldn't do before. Even 20 years ago was unthinkable, and now it's kind of an everyday thing. So it's in much the same way that when Galileo discovered or first used the telescope to look at the night sky, and how it changed the way we look at the night sky because he could see things that we couldn't see with the naked eye. Radio astronomy has done the same thing. In the early 1900s, there was some radio astronomy in 1930s, 1950s, and we had some basic stuff. But now that we have high resolution telescopes and a lot of ability to process all of this data, we can now basically have radio telescopes that give us fine details and let us see an entire universe of radio phenomena. So that's kind of the biggest thing. Are there any, do you have any questions or anything and specific things you want to know about? Or?
I'd be interested in it.
You what?
What got you interested in the subject to pursue it as a career?
I've always been fascinated by the night sky. And so when I did my doctorate degree, my dissertation was actually on black holes. And at the time when I did my dissertation, we strongly suspected that black holes were real, but we didn't have any direct images of them. And the reason for that is because black holes tend to be surrounded by a lot of gas and dust, and that makes them hard to see. And so one of the really powerful things about radio astronomy is that it can see through the gas and dust. So we can actually study black holes in a way that we couldn't do otherwise. Another part of black holes, particularly ones that are kind of really far away, many of them are very active. They're consuming matter at a massive rate. And so they give off a lot of light. Some of it's high energy X-rays and stuff, but they also give off a lot of radio light. And so radio telescopes can actually look at these sources and study how black holes consume matter and how they change the way galaxies behave and things like that. So it's really connected to kind of the black holes and stuff that I was always interested in.
What can you tell us about dark matter?
Dark matter is interesting because dark matter is one of those things that's being looked at from various different ways. So in general, most of the evidence that we have from dark matter is from visible light. We can see how stars move in a galaxy and how that would tell us what the distribution of mass is in a galaxy. And it was one of the first clues that there was more matter there than we were seeing. And so that gave rise to the idea of dark matter. But with radio astronomy, there's, I'm gonna forget the name. There's a Canadian radio telescope that is like this long parabolic dish. It's very different from other ones. And I can't remember the name of it at the moment, which is embarrassing. But what it's doing is it's mapping out where hydrogen is in the universe, in interstellar and intergalactic space. The interesting thing about hydrogen is that hydrogen gives off a very specific radio signal that's called the 21 centimeter line. And the reason is because its wavelength is 21 centimeters long. But hydrogen is the one thing that does this. So if you find this signal, you know it's hydrogen because nothing else makes that signal. And so you can listen to this radio signal and find out basically where the hydrogen is in the universe. The reason that's important is because it would tend to clump together where there is dark matter. So if you map out where all the hydrogen is in interstellar space, you kind of have a map of where dark matter is. And that tells us something new because we know that like dark matter should be out there, but we don't know what it's made of. And we don't know how it interacts even with itself. Like we know how regular matter interacts with itself and creates temperature and pressure and pushes against itself and all of that. We don't know what dark matter does. Dark matter doesn't interact with light, but does it collide with itself? Can it clump into large chunks? We don't know. And so by mapping out where the hydrogen is, we can help to understand kind of what dark matter would be. And so that's a big thing that's now happening. And we're getting more detailed information like that because of radio astronomy.
Wow. Very interesting.
Yeah, you've explained it well.
You did, because we were starting, at least I was starting with absolutely no knowledge, and now I know a lot.
Yeah. So, I mean, I could talk a little bit about one of the challenges that we're starting to face, and that is, with regular astronomy, you might be familiar with light pollution. That basically, you live in a suburb, you're not really going to see a really dark sky. You have to go out in the middle of nowhere The same type of thing happens with radio astronomy. Not because the Earth itself creates a lot of radio noise, but because we do. So there are a lot of the radio telescopes are in remote areas, and they have to be in remote areas because if they're close to a large city or something, all of the cell phones and the cars and the radio stations are all emitting this radio noise that makes it harder for the telescopes to study the night sky. So that's a challenge. One of the things that's happening now is you're getting satellites that are going to be used for, internet, for example. If you've heard of Starlink, for example, Elon Musk wants to put up a whole bunch of satellites orbiting the Earth that are all going to have these radio signals so we can all get high-speed internet, which is cool. But at the same time, that means that when a radio telescope looks up in the night sky, it's going to see a whole bunch of these satellites going overhead, which creates more light pollution in radio light. And so one of the big challenges is we've kind of just reached this new technology to see things in high resolution. And now other projects are creating more radio noise that makes it harder to overcome. How do you deal with that? That's still an ongoing challenge. It's something we haven't solved yet.
Maybe we ought to put a dish on the moon.
There is talk on that, as they say in radio astronomy, if you give me $500 billion, that's exactly what I'm going to do. It's kind of the ultimate goal, is to put one on the moon, on the far side of the moon, so it wouldn't get any Earth radio noise. That would be amazing. But we don't have a base on the moon, and we'd need a base on the far side of the moon to maintain the telescopes. Because you'd need hundreds and hundreds of antennas, and they have to be fixed sometimes. So you'd have to have people living on the moon to take care of your radio observatory, which again would be cool, but there's a budget issue.
Someday, maybe.
Someday, yeah. There are plans out there about how we might do that. There are a couple of radio telescopes in space now. They're very simple. Doing something like a array of antennas on the moon is something that we definitely want to plan for, and there are ideas, but they're still kind of in the far future. Maybe 100 years from now, we might have a radio telescope on the far side of the moon. But yeah, that would be awesome. I would love to see that.
So don't pack your bag yet, huh?
No, not packing my bag yet. They'll probably still have me working from Earth, even if I am working for them. So, any other questions or things?
Any questions?
No?
No, I think we gave you some good ones.
Okay, good. So, yeah, if you're ever interested in seeing a radio telescope, there are several across the country. In West Virginia, there is Green Bank Observatory. It's in the hills of Appalachia, and they have a visitor center and give tours. That's where the largest steerable telescope is. If you make it out to New Mexico, the Very Large Array, which is about 35 miles west of Socorro, you can go out to New Mexico and see the Very Large Array, and they have tours when they're open. They're not open now because of the containment, but when they're open, they have a tour every other Saturday in the month. And so those are a couple just in the United States that you can see that are active and working radio telescopes.
Okay.
So,
Great.
yeah. Okay.
Thank you.
Yep.
Thank you,
Well, I
Brian.
hope you've enjoyed it. And
I did. Very interesting.
if you have any other questions, contact the library. They know where I live. So
Okay.
at least one of the librarians knows where I live. So
Right. Great. Thank you.
okay. Thank you.
All right, you can go ahead and end it.
Okay. Just end meeting.
Just say goodbye.
Okay. We're saying goodbye. Hope you
Bye.
enjoyed watching it.
Yeah, we did.
In the meeting.
End meeting, and then you have
Okay.
to. Okay.
Okay.